Welcome to this problem walkthrough. Today, we will dive into LeetCode problem number 1740, find distance in a binary tree. In this problem, we are tasked with calculating the distance between two nodes in a binary tree, measured by the number of edges between them. This is a classic binary tree problem that tests your understanding of tree traversal and lowest common ancestor (LCA) concepts. Let's explore the problem and break it down step by step. In this problem, you are given the root of a binary tree along with two integers, p and q, which represent the values of two nodes within the tree. Your task is to determine the distance between these two nodes. The distance, in this context, is defined as the number of edges along the shortest path connecting the two nodes. For the input, you'll receive the root of the binary tree as a tree node, which is guaranteed to be a valid binary tree, and the integers p and q, which are guaranteed to represent values of nodes that exist in the tree. The output should be a single integer representing the distance between these nodes. Let's look at some examples to clarify the problem further. For the first example, the input consists of a binary tree represented as root equals 1, 2, 3, 4, with p equals 2 and q equals 3. The tree structure looks like this. The root node has a value of 1, with two children, 2 and 3. Node 2 itself has a left child with a value of 4. To calculate the distance between nodes with values 2 and 3, we find the shortest path connecting them, which is 2 to 1 to 3. This path passes through two edges, so the output is 2. Here, we can see that the shortest path between nodes 2 and 3 consists of exactly two edges. Now, let's consider another example. The input for this case is root equals 1, 2, 3, null 4, with p equals 2 and q equals 4. The tree structure here is slightly different. The root node 1 has two children, 2 and 3, but this time node 2 has a right child with a value of 4. To determine the distance between nodes 2 and 4, the shortest path is a direct connection from 2 to 4. This path contains just one edge, so the output is 1. In this second example, the explanation is straightforward. The shortest path between nodes 2 and 4 is simply from 2 to 4, which involves only one edge. Now, looking at the third example, the input is root equals 1, 2, with p equals 1 and q equals 2. The tree consists of just two nodes, where the root node 1 has a single left child with a value of 2. The shortest path between nodes 1 and 2 is the direct edge connecting them. Since this path contains exactly one edge, the output is 1. In this example, the shortest path between nodes 1 and 2 is again direct, consisting of just one edge. This highlights a key scenario where the nodes are directly connected in a parent-child relationship. Now, let's consider additional constraints and edge cases for this problem. The binary tree can have up to 10,000 nodes, with each node's value being a unique integer between 0 and 1 billion. You are guaranteed that p and q exist in the tree, and their values are distinct. These constraints ensure that your solution must handle large inputs efficiently. There are a few critical edge cases to consider when solving this problem. First, in a small tree with only two nodes, such as root equals 1, 2, where p equals 1 and q equals 2, the output should be 1 because the nodes are directly connected. Another edge case involves deep tree structures, where the nodes p and q are located far down the tree. Your solution must efficiently handle these depths without excessive computation. Finally, if p and q share a common ancestor that is far from the root, your solution must correctly calculate the distance by considering the path through this common ancestor. Addressing these edge cases will ensure your solution is robust and performs well across all scenarios. To solve the problem of finding the distance between two nodes in a binary tree, we can break the task into three essential steps. First, we need to determine the lowest common ancestor, or LCA, of the two nodes. The LCA is the deepest node in the tree that serves as a common ancestor to both nodes. Once we have the LCA, the next step is to calculate the depth of each node p and q relative to this LCA. Finally, the total distance is simply the sum of these depths. One straightforward way to approach this is the brute force method, where we find the paths from the root to each node individually. By comparing these paths, we can identify the LCA as the last common node. After that, the distance can be computed by summing the differences in path lengths from the LCA to p and q. However, this approach requires traversing the tree multiple times, making it less efficient, especially for larger trees. The time complexity for this brute force method is O(n) squared, in the worst case, as finding paths involves repeated traversals. Space complexity is O(h), where h is the height of the tree, to account for the recursion stack during depth-first search. An optimized approach significantly improves on the brute force method by eliminating redundant tree traversals. In this approach, we use a single traversal to simultaneously find the LCA and calculate the depths of nodes P and Q relative to it. This can be achieved using a recursive helper function that traverses the tree. During the traversal, the function identifies the LCA when one subtree contains P and the other contains Q. At the same time, it tracks the depths of P and Q relative to the LCA. Once the traversal is complete and the LCA is found, we can directly calculate the total distance by summing the depths of the two nodes. This method is more time efficient, with a time complexity of O(n), since the tree is traversed only once. The space complexity remains O(h), as we still need to account for the recursion stack. This approach minimizes computational overhead and is well suited for larger trees. Another possible method involves pre-computing parent pointers for all nodes in the tree. This approach allows for efficient upward traversal to locate the LCA and compute distances. To implement this, we first perform a breadth-first or depth-first search across the tree and store parent pointers for every node. Once these pointers are pre-computed, we can quickly build paths from nodes P and Q back to the root. By comparing these paths, we can identify the LCA as the last common node. With the LCA determined, calculating the distance becomes straightforward. While this approach is efficient in terms of time, requiring O(n) for pre-computing parent pointers and O(h) for finding the LCA, it introduces additional space overhead. Specifically, we need O(n) space to store the parent pointers for all nodes in the tree. This makes the method particularly useful in dynamic tree scenarios where multiple distance queries are required, but it may not be necessary for a single query problem like this one. For this problem, we chose the optimized approach of finding the LCA and calculating depths in a single traversal. This strategy offers the best balance between time and space efficiency, avoiding redundant tree traversals and minimizing storage overhead. A key observation here is that the LCA is central to solving the problem efficiently, as it serves as the branching point for the shortest path between the two nodes. By combining the LCA search with depth calculation in a single traversal, we can leverage recursion to streamline the process and avoid unnecessary computations. This method is not only time efficient, with a complexity of O(n), but also space efficient, requiring only O(h) space for the recursion stack. These qualities make it the ideal choice for large trees, where efficiency is critical. While the brute force approach is simpler conceptually, it is computationally expensive for large inputs. Similarly, the parent pointer approach, while useful for dynamic trees, adds storage overhead that is unnecessary for a single query problem. Overall, the optimized approach strikes the perfect balance, ensuring both clarity and scalability. In conclusion, the optimized approach of combining LCA identification and depth calculation in a single traversal is the most effective strategy for solving this problem. It provides an excellent combination of speed, memory efficiency, and simplicity in implementation. This makes it highly scalable and well-suited for large binary trees. By eliminating redundant computations and keeping the solution straightforward, we achieve an efficient and elegant method to determine the distance between two nodes in a binary tree. In this problem, we aim to calculate the distance and edges between two nodes, P and Q, in a binary tree. To achieve this efficiently, we leverage the concept of the lowest common ancestor, or LCA. The LCA is the deepest node in the tree that is an ancestor of both P and Q. Once we find the LCA, we can determine the distance by calculating the depth of each node relative to this common ancestor. The first step in our algorithm is to find the LCA. The intuition behind this is that the LCA splits the path between P and Q into two disjoint sections, one from P to the LCA and the other from Q to the LCA. To find the LCA, we use a recursive approach. If the current node is null, we return null as the base case. If the current node matches either P or Q, we return the current node since it is part of the path. Otherwise, we recursively search for P and Q in the left and right subtrees. If both subtrees return non-null results, it means the current node is the LCA because the nodes are found on different sides. If only one side is non-null, we propagate that result upwards. This recursive approach ensures that the LCA is found in n time, where n is the number of nodes in the tree. After determining the LCA, the next step is to calculate the depth of each node relative to it. Starting from the LCA, we use a recursive helper function to traverse the tree and find the target node. At each step, we increment a depth counter and pass it along the recursive calls. Once the target node is found, the function returns its depth relative to the LCA. This method works because the depth represents the number of edges in the path from the LCA to the target node. Finally, we compute the total distance between P and Q by summing their depths from the LCA using the formula, distance, P, Q, equals depth, P, LCA, plus depth, Q, LCA. This gives us the total number of edges between the two nodes. The algorithm then returns this computed distance as the result. Using the LCA is crucial because it simplifies the problem by dividing the path between P and Q into two separate paths. This eliminates redundant traversals and avoids unnecessary computations, making the algorithm efficient. In terms of complexity, finding the LCA takes n time, and calculating the depth for each node also takes n. Therefore, the overall time complexity of the algorithm is n, where n is the total number of nodes in the tree. The space complexity is h, where h is the height of the tree, due to the recursive call stack. For a balanced binary tree, the height is log n, making the space usage logarithmic in such cases. The binary tree itself is the input structure, where each node has pointers to its left and right children. Additionally, the recursive approach relies on the call stack to manage the traversal, which accounts for the h space complexity. It's important to consider edge cases to ensure the algorithm is robust. First, if one or both nodes, P or Q, are not present in the tree, the algorithm should handle this gracefully by returning -1 or throwing an appropriate exception. If the nodes are the same, meaning P equals Q, the distance is 0 because the path length is 0. For unbalanced trees, the algorithm still works correctly since it does not assume the tree has any specific structure. Finally, for a null tree, where there are no nodes at all, the algorithm should return -1 or an appropriate error message. The code implementation starts with defining the treenode class, which represents a single node in the binary tree. The findLCA function is then implemented to recursively find the lowest common ancestor of P and Q. If the current node is null or matches P or Q, it is returned. Otherwise, the function searches both left and right subtrees. If both sides return non-null results, the current node is the LCA. Otherwise, it propagates the non-null result upwards. The findLCA function concludes by returning the result from either the left or right subtree, depending on which is non-null. Next, the findDepth function is defined to calculate the depth of a target node relative to the current root. If the root is null, the function returns -1. If the root matches the target, it returns the current depth. Otherwise, it recursively searches the left and right subtrees, incrementing the depth counter. The function returns the depth as soon as the target node is found. Finally, the findDistance function ties everything together. It first calls findLCA to get the common ancestor of P and Q. If no LCA is found, it returns -1. Otherwise, it calculates the depth of P and Q from the LCA using the findDepth function. The total distance is the sum of these depths, which is returned as the final result. This implementation ensures correctness and efficiency while handling various edge cases appropriately. Here, we begin by defining the findDistance method inside the solution class. The goal of this method is to calculate the distance between two nodes, P and Q, in a binary tree. To achieve this, we implement two helper functions. The first helper function, find_LCA, is used to locate the lowest common ancestor, or LCA, of the two given nodes. The LCA is the deepest node in the tree that is an ancestor to both P and Q. If the current node is null or matches either P or Q, it is returned as a potential LCA. Otherwise, we recursively traverse the left and right subtrees to check where P and Q are located. If both subtrees return a non-null value, the current node is the LCA. If only one subtree is non-null, it means both nodes lie in that subtree, and we propagate that result upwards. The second helper function, find_distance_from_node, calculates the distance from a given node to a target node. Starting from the input node, it traverses the tree recursively while maintaining a counter for the distance. If the target node is found, the current distance is returned. If the target isn't on one side of the tree, the function continues searching the other side. With these two helper functions, we can now compute distances in the binary tree effectively. First, we call find_LCA to find the LCA of P and Q. After determining the LCA, we calculate the distance from the LCA to each of the nodes P and Q. Using the find_distance_from_node helper function, we pass the LCA as the starting point and compute the distance to P, storing it in distance_P. Similarly, we calculate the distance to Q and store it in distance_Q. Finally, we return the sum of these distances, which gives us the total distance between P and Q in the binary tree. This approach ensures that the calculation is efficient and leverages the properties of the LCA to minimize redundant traversals. By combining the results of these helper functions, the solution is both clean and easy to follow. Here, we define the main method, findDistance, which calculates the distance between two nodes in a binary tree. The first step is to find the lowest common ancestor, or LCA, of the two nodes, P and Q. This is done using the helper method findLCA. Once we have the LCA, we calculate the distance from the LCA to each of the nodes separately using another helper method, findDistanceFromNode. Finally, the total distance between the two nodes is simply the sum of these two distances. In the findLCA helper method, we recursively search for the nodes P and Q in the left and right subtrees of the current node. If both left and right subtrees return non-null values, the current node must be the LCA. Otherwise, we return the non-null subtree, or null if neither subtree contains the nodes. Next, we have the implementation of the helper method findDistanceFromNode, which calculates the distance from a given node to a target node. This method starts by checking if the current node is null, in which case it returns -1 to indicate the target is not found in that path. If the current node matches the target value, it returns the accumulated distance. Otherwise, it recursively checks the left and right subtrees, incrementing the distance by 1 at each step. If the target is found in the left subtree, the left distance is returned. Otherwise, the method proceeds to check the right subtree. At the end, we also define the treenode class, which represents the structure of each node in the binary tree. Each node stores its value and pointers to its left and right children. Finally, the closing braces complete the treenode class and the solution class. This wraps up our implementation, which includes the main method to find the distance between two nodes, as well as all the necessary helper methods and data structures. With this setup, the solution is efficient and handles the recursive traversal of the binary tree to compute the result. To solve this problem, let's start with example 1, where the binary tree has the structure shown, and we need to find the distance between nodes 4 and 5. The first step is to find the lowest common ancestor, or LCA, of nodes 4 and 5. Starting at the root node, which is 1, we see that it doesn't match either of the target nodes. So, we traverse the left subtree, reaching node 2. At node 2, we again find no match, so we continue exploring both its left and right subtrees. The left subtree leads us to node 4, which matches one of the target nodes. Similarly, the right subtree leads us to node 5, which is the other target node. Since both subtrees of node 2 contain one of the target nodes, node 2 is identified as the LCA. Next, we calculate the distance from the LCA to node 4 by traversing the left subtree of node 2, which leads directly to node 4 at a distance of 1. Now, we determine the distance from the LCA, node 2, to node 5. Traversing the right subtree of node 2, we directly reach node 5, which is at a distance of 1. With both distances calculated, we add them together to find the total distance. The distance from the LCA to node 4 is 1, and the distance from the LCA to node 5 is also 1. Adding these, the total distance between nodes 4 and 5 is 2. The output for this example is therefore 2. Moving on to the second example, we consider nodes located at different depths in the tree. Here, the goal is to find the distance between nodes 4 and 3, with the binary tree structure remaining the same. To solve this, we start by finding the LCA of nodes 4 and 3. Beginning at the root node, 1, we observe that it doesn't match either of the target nodes. We then traverse the left subtree, reaching node 2. At node 2, we again find no match and proceed to explore its left and right subtrees. The left subtree leads to node 4, which matches one of the target nodes, but the right subtree does not yield a match. Returning to the root node, we then traverse the right subtree and find node 3, which matches the second target node. Since both the left and right subtrees of the root node contain one of the target nodes, the root node, 1, is identified as the LCA. Next, to calculate the distance from the LCA to node 4, we traverse the left subtree of the root to node 2, which is at distance 1, and then from node 2 to node 4, which is an additional distance of 1. This gives a total distance of 2 from the LCA to node 4. For the distance from the LCA to node 3, we traverse the right subtree of the root directly to node 3, which is found at a distance of 1. Adding the distances, the total distance between nodes 4 and 3 is 2 plus 1, which equals 3. The output for this example is 3. Now, let's look at a third example where the two nodes are located in the same subtree. Here, we are tasked with finding the distance between nodes 5 and 6. The binary tree structure includes an additional node, 6, as a left child of node 5. We start by finding the LCA of nodes 5 and 6. Beginning at the root node, 1, we see that it doesn't match either of the target nodes, so we traverse the left subtree to node 2. At node 2, we also find no match and continue exploring its left and right subtrees. The left subtree leads to node 4, which does not match, while the right subtree reaches node 5, which matches one of the target nodes. From node 5, we further explore its left subtree to find node 6, which matches the second target node. Since both the left and right subtrees of node 5 contain one of the target nodes, node 5 is identified as the LCA. The distance from the LCA to node 5 is 0, as it is the same node, and the distance from the LCA to node 6 is 1, as we traverse its left subtree. Adding these distances, the total distance between nodes 5 and 6 is 0 plus 1, which equals 1. The output for this example is 1. To analyze the time complexity of our solution, we break it down into two main steps: finding the lowest common ancestor, or LCA, and determining the distance from the LCA to the nodes P and Q. First, the find_LCA function uses a depth-first traversal to locate the LCA. This traversal visits each node in the binary tree once, so in the worst case, when the tree has n nodes, this step has a time complexity of O(n). Next, we need to calculate the distance from the LCA to the nodes P and Q. This is done using the find_distance_from_node function, which also performs a depth-first traversal, starting at the LCA and moving downward until the target node is found. Since this process is repeated twice, once for each node, its work is proportional to the size of the subtree rooted at the LCA. However, because the LCA is part of the overall tree, the combined work across both calls is still O(n) in the worst case. Now, combining the time complexities of these two steps gives us the overall time complexity. The find_LCA function takes O(n), and the two calls to find_distance_from_node also take O(n). Since these operations are performed sequentially, their combined time complexity is O(n) plus O(n), which simplifies to O(n). Shifting to space complexity, the primary contributor is the recursive call stack used by both find_LCA and find_distance_from_node. The maximum depth of recursion corresponds to the height of the binary tree, denoted as h. In a balanced tree, h is proportional to log n, but in the worst case, such as a skewed tree, the height can reach n. Thus, the space complexity of the recursive stack is O(h), which in the worst case becomes O(n). Importantly, no additional data structures are used in this implementation, and all computations are performed in place. Consequently, the overall space complexity is also O(h), which simplifies to O(n) in the worst case. When comparing this optimized approach to a more naive or brute force method, we can see clear advantages. A naive solution might involve finding the paths from the root to the nodes P and Q, storing these paths in lists, and then comparing the two lists to identify the lowest common node. While this approach also has a time complexity of O(n), it incurs additional space overhead for storing the paths, leading to a space complexity of O(n). In contrast, the optimized solution avoids storing paths altogether, directly calculating the LCA in distances. This reduces the space usage significantly, making the approach more efficient while maintaining the same time complexity of O(n). The efficiency of this solution can also be understood by considering the best, average, and worst cases. In the best case, when P and Q are close to the root, for instance, if one of them is the root itself or its immediate child, the traversal depth is minimal. While the time complexity remains O(n), due to the LCA search, the actual number of operations performed is significantly reduced. In the average case, such as in a balanced binary tree, the traversal depth is proportional to log n. However, because the algorithm must still visit all nodes in the worst case to ensure the LCA is identified, the asymptotic time complexity remains O(n). Finally, in the worst case, which occurs in a skewed tree, the height of the tree equals the number of nodes, n. Here, all nodes may need to be visited, leading to a time complexity of O(n) and a space complexity of O(n) due to the recursive call stack. To solidify our understanding, let's consider the mathematical proof for the big O complexity. The find_LCA function ensures that each node is visited exactly once during its traversal, leading to a time complexity of O(n). Similarly, the find_distance_from_node function traverses nodes within a subtree, but since it is invoked twice, once for P and once for Q, the total work done remains O(n). Combining these operations sequentially results in an overall time complexity of O(n). On the space complexity side, the depth of recursion dictates the maximum memory usage, which corresponds to the height of the tree, O(h). In the worst case, when the tree is skewed, the height becomes n, leading to a space complexity of O(n). This analysis confirms the efficiency of our approach in terms of both time and space. One of the most common mistakes people make when solving this problem is confusing distance with depth. Remember, depth refers to how far a node is from the root, while distance is about the number of edges in the shortest path between two nodes. To calculate distance, you need to consider the lowest common ancestor, or LCA, as it plays a key role in determining the shortest path. Another frequent issue is implementing the LCA algorithm incorrectly. Some solutions fail to account for edge cases, like when one of the nodes isn't in the tree, leading to wrong results or inefficiencies. It's crucial to ensure your LCA algorithm is robust. Additionally, many people overlook edge cases entirely. For example, when P and Q are the same node, or when one of them happens to be the root, these scenarios can break your solution if not handled carefully. Inefficient traversals are another pitfall. Unnecessarily traversing the entire tree multiple times can inflate your time complexity. A smarter approach combines tasks, such as finding the LCA and calculating distances, in a single traversal. Lastly, some assume that both nodes P and Q will always exist in the tree without validating their presence, which can lead to runtime errors. Always validate the input to avoid these issues. Now, let's focus on what interviewers typically look for. First, make sure you have a strong grasp of tree fundamentals, like depth, height, and the concept of the LCA. Interviewers may probe your understanding with follow-up questions, so be ready to explain these concepts clearly. Efficiency often takes center stage, so aim for an O(n) solution by combining the LCA and distance calculations into a single traversal. Redundant traversals can be a red flag. It's also important to proactively address edge cases. Discuss scenarios like missing nodes, imbalanced trees, or when P and Q are the same node to demonstrate thoroughness. Another area to prepare for is the difference between recursive and iterative approaches. While recursion is often easier to write and understand, it can lead to stack overflow in very deep trees. Understanding both methods shows flexibility. Finally, it's a good idea to practice related problems. For example, problem 236 focuses on finding the LCA, which is a key building block for this problem. Problem 543 deals with calculating the diameter of a binary tree, which also involves tree traversal and distance calculations. Similarly, problem 1123 tests your LCA knowledge in a more specific context, while problem 124 emphasizes path calculations. Mastering these will strengthen your problem-solving skills. Let's explore some alternative approaches and the trade-offs involved. One option is pre-processing the tree to store parent pointers for each node. This allows you to find the LCA in constant time and calculate distances with minimal traversal. However, the trade-off is higher memory usage and the need for pre-processing, which can be a drawback depending on the problem constraints. Another approach is to use BFS instead of the more common DFS. BFS is iterative, which avoids the risk of stack overflow in deep trees. However, it often requires additional bookkeeping, such as tracking levels or parent relationships, which can make the implementation slightly more complex. For those dealing with very large trees, advanced techniques like binary lifting can be employed. Binary lifting enables you to find the LCA in O log n, which is incredibly efficient. However, this approach is typically overkill for most interview scenarios and requires a deeper understanding of pre-processing and sparse tables. While these alternatives can be useful, it's essential to weigh their complexity against the specific requirements of the problem at hand. Great job making it through the problem. In summary, we use tree traversal and LCA concepts to solve the find distance in a binary tree problem efficiently. Remember, understanding tree structures and their traversal techniques is vital for tackling similar challenges. Thanks for watching, and we hope to see you in the next video. Don't forget to like, subscribe, and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!